Alright guys, thanks for coming. We're going to go ahead and get started. Our speaker this week is Mark Borrelli. He's an associate research scientist at the Center for Coastal Studies in Provincetown, Mass. He's also a research faculty at the School for the Environment at the University of Mass in Boston. His research interests include coastal sedimentary processes in general, and also understanding how storms, sea level rise, and anthropogenic impacts affect the coast in particular. Recent and ongoing research includes mapping the seafloor and shallow coastal waters, studying bed forms and sediment transport in the nearshore, understanding the morphodynamics of tidal inlets, and quantifying change in salt marshes.
All right, thanks very much. Just jump right in. I thought what I would do first is just talk a little bit about the Center for Coastal Studies. We were founded in 1976. Back then it was primarily whales with a little bit of coastal geology mixed in. We basically developed the method to disentangle marine animals back in the late 70s, early 80s. And we now train people from all over the world. We have a couple people at the center who are in the International Whaling Commission, so we do a lot of marine mammal research and rescue. Let's see, we three main departments, mine, population biology, and ecology, with programs in each one. We have about 25, 30 full-time people, about another 10 or 15 part-time staff, and an influx of interns and grad students in the summer and things like that. And we have a lot of smaller programs. Some of these, the marine entanglement response team is about 5 or 6 people. It's its own little program, and then you have other programs. Some of these are 1 or 2 people programs, and other are larger. But just a real brief overview of who we are and what we do. This is our customized shallow draft research vessels, the RV Marindin, named after Henry Marindin. He was one of the first guys in the early, mid to late 1800s who understood that you needed to map the land and the ocean as one system. So we thought it'd be a really good idea to name this boat after him. Because that's what we're trying to do. We're trying to map that white space, that really, really shallow area that links the land and the ocean. 27-foot eastern. It's a nice. I'm going to show off my PowerPoint chops right here. This is our system. We lower it down, we lock it into place, we go, we pick it up, and we're off. That's about it for my PowerPoint stuff. But it's a really good vessel. As you can see, we are often in the green part of the nautical charts when we map these things, and we go very, very shallow. This is when I lean toward the back of the boat. But this is where we work. This is what we want to do. This is the EdgeTech 6205. When we first started, I started in 2009. We had a 3-year project with the state. And we were able to buy a Teledyne Bentho C38. I don't really want to say too much about this particular instrument, but EdgeTech 41. This is a traditional Sidescan we got a couple of years ago. Very, very. It's a workhorse. Always works. And we just got the EdgeTech 6205 last year. Cannot say enough about this. It's fantastic. Really, really works, and especially after coming after the C3D, night and day. And we have a MRU, typical stuff, a vector sensor, and we have real-time kinematic GPS on the boat. One of the things we do is we subscribe to a proprietary network that allows us a virtual base station, basically. So we have real-time kinematic without a base station. We don't need to set up a base station on land, and there's no post-processing. So through a cellular network, we get real-time GPS, we get off the boat, and our data are all set. We don't have to post-process to get for any kind of correction, as long as you have cell reception. But we're so close to the coast, we usually do. Yeah, what's in a name? Just really quick. I probably don't have to talk to too many folks about this here, but interferometric sonar, right? It's not really interferometric, right? There's no interference fringes. We're not really counting the high and the low or anything like that. I think you guys call it, or a lot of people call it phase differencing bathymetric sonar. Now, to my mind, the modifier, you don't need the bathymetric. If it's phase differencing, you get bathymetry. So I don't know if you need that modifier. I used phase measuring Sidescan sonar, or phase differencing, that's fine. But I'm going to call it phase measuring Sidescan sonar throughout the talk. This is the one and only slide you're going to see from the C3D. Now, it's 200 kilohertz. The Sidescan was pretty good. I have to give it credit. This, for a 200 kilohertz system, that's not bad. This is eelgrass, very shallow water. It's pretty good. It's really dense. We're not getting any kind of penetration at 200 kilohertz, so it was pretty good. And this is the intertidal stuff, just from that same area, not the same exact place, but the same area, just to give you a sense of that particular instrument. You won't be seeing any bathymetry from that instrument here today. I'm trying to impress. All right. So what I'm going to do, I'm just going to walk you through a couple projects that we're doing, right? This is a really unique project in Wellfleet. If you guys ever heard of Wellfleet oysters, or ever had Wellfleet oysters, huge business for the town, millions of dollars. I think it's $3 million a year. A lot of oysters. So I just want to tell you about a really unique project the University of Massachusetts Boston and the center are working on. Basically what they've done is this red polygon. They have it's a 2-acre site, and they are planting oysters. They're seeding the area, putting down a culch, which is just shells, to give it a hard substrate so the oysters will grow. They're going to let them grow just to improve water quality. So it's a really unique idea. They've been doing this for a while. They've been doing it since 2010 or 11, I think. So this is propagation site. Now we're just north. Let me just go back. We're just north of that. Oh yeah, I have this somewhere. Sorry. So that's the propagation site. It's about 2 acres. This is the pier. This is the propagation site. Now we're looking back at the pier, and it was nasty, right? It's nothing's growing here. It's really kind of a nasty place. So what they did was really unique idea. They got this. It's just basically the same thing you would have at a sander, right? They put sand on the road from the back of a truck, and they put shells. They put quahog shells in here. They put it on a barge, and they move it around, and they get all these rows, and they call it culch, these culch mounts. So what do? They put down this substrate, and they get a lot of quadrats, do a lot of counting, and they want to see the oysters, right? They want to see how many oysters, how much spat is attaching to the shell, and it's working. It's working really, really well. They've grown, by their estimates, based on the quadrat, about 2 million oysters in this area. So it's really working well. But now what they wanted us to do is come in and map, do some Sidescan Sonar, and map the areas and see how much culch they actually put down, how many acres, that kind of thing. But like I said, as you can see, they're growing really, really well. Now we're not going to eat these, although there are reports of folks wandering in and picking when they're not supposed to be. But so this is an interesting spot here. So what they've done now, again, they've done this for a couple of years. This is from 2012. And what you can see here, we'll zoom in a little. You see growth here from the old culch mounds, and this is the new one just from that year. So you got growth here, and just the quahog shells here. So this is with the 4125, the 1600, the high frequency, and it's really nice. And we're actually seeing individual shells here. And you can actually see individuals, and which is it's not that surprising. 1600 is really high frequency, really shallow water. But what we started to do, we started to think about this when we went to other places in the harbor. These are all oyster beds right in here. It's all natural growth. So I started to get this idea, can we start to count oysters using Sidescan? Quadrat method is fine, but if we could do it subtidally using a Sidescan Sonar or something similar, then you can start to have a tool that Shellfish, the Nature Conservancy, and other groups who do this kind of thing would really like. So, some more PowerPoint skills there. Okay, so we have oysters here growing in life position, and then you have just the quahogs, the new ones. Same kind of substrate, you're going to get the same reflection, you're going to get the same intensity return, more or less. But the question is, can we tell the difference between these two areas? Can we see the difference between adult oysters in life position and the flat ones? So what we started to do is we started to think about how we would do this. So we got an area here, and I just started to look at these mounds and started looking at intensity values. Started to understand if we can change this. Now this is literally me just fooling around with these pictures to try and get what I know we have. So we can go out and walk these in the intertidal area and say, okay, this mound has live oysters, and this one doesn't. So we can now start to tease out whether what we're seeing is live, these oysters in life position, or it's just that culch, the flat culch, it hasn't any, there's no growth on it yet. And we'll see if we can start generating population numbers. And we just started this actually, because what we did this year with the 6205 is we had a bathymetry component to it. Right? So this is a 25-meter range, 50-meter swath, very shallow water. We got our bathymetry. Now this bathymetry is about 13 meters wide and about 2 meters of water. So you get about 7:1, 6:1 swath, and it's clean. And the overlap's really good. And the features are tiny. And it's 10, 15 centimeters, and we're seeing it. So the bathymetry works really well. Yeah, it's a little noisy, but this is a really flat area. So can we start to look at using the 6105 and 6005 and start to realize or start to get at area covered, how many shells are mapped on the bottom? That's relatively easy. But can we start to tell the difference between live oysters and not, or no growth yet?
Yeah. Your Bradley data is the bin data out of the 6205, is that right?
Yes.
And what bin size did you choose out of curiosity?
I think for this we did 10 centimeters, 5 centimeters, really tight. Obviously you're talking about a lot of data if you're going to a big area, but this is what they want. So we're just starting to figure out we're looking at. But you can see even the far field, the stuff's pretty good. You still see the feature. Didn't do this in Fledermaus because Fledermaus is not kind to sort of low relief. It looks really noisy, so we just did it on jigs. All right, so go back to this picture again. 200 kilohertz. Now we're looking at it with the phase measuring sonar in different area. And this is, we see this, we're getting this a lot. When we want to look at areas and we want to map them, with temperature can give you a lot of information, right? We go back, we see this eelgrass, and then we see this feature. Now, if it's just side scan, you might not know what that is. You can get a little information from the raw signal. What we've got here is a migrating sand sheet that's burying this eelgrass. So the ability to map at the same time the telemetry and the imagery, the backscatter, is really powerful. And even though it's a very narrow swath, it gives you that information. That this is higher, that's lower, the eelgrass is getting buried, and then you've got the sand sheet, a little eelgrass, and then it's flat again. So there's a lot of information here that we can use. And what's another interesting thing, and this is from this year also, is that it's a much higher frequency that we're looking at with the eelgrass, but we're seeing things in the eelgrass at a higher frequency. Let me just go back. We don't know what these are. We don't know if they're shells. We don't know if this is growth on the eelgrass here. We don't know what they are. It's a higher frequency. You probably shouldn't penetrate as well, right? But it's pretty thick. Can't see the seafloor in a lot of places, but we're seeing these reflectors. And again, it's another thing we want to go out and start to look at and see if we can get a handle on what these actually are. So this is the side scan. And there's another one in P-Town, in Provincetown Harbor that we looked at. But what I wanted to do is jump out and look at the bathymetry. Do this with the, so it's just the one line here. You can see that. Okay. And we've got the bathymetry here, and we're picking up the eelgrass. And the eelgrass, again, that co-location works really well. So we're getting the changes in the eelgrass. Now I think what this is, this is a function of how Fledermaus is processing this data, just smoothing it out. It's a real sharp contact in the bathymetry, and in the bathymetry in Caris. When you see it in Caris, it's a really sharp contour. But here, I think Fledermaus is just rounding out. So this is the edge of your eelgrass right in here. So now you start to think, or I start to think about some of the things you could look at using this phase measuring sonar. You don't have two disparate data sets. This backscatter image is much better than the backscatter from multi-beam, so you're getting all kinds of information here that you normally wouldn't be able to get or get as easily using other systems. And when we did this with the C3D, the co-location really wasn't there. Had all kinds of timing problems. This is right on the money. It's phenomenal. We see it time and time again with this instrument. So now we can start looking at different metrics when we start looking at eelgrass, things that would be much more difficult in other areas. Couldn't get that right in PowerPoint, so I wanted to jump on. You guys are familiar with Fledermaus, right? Mm-hmm. Get it. Okay. All right. So another one that we'll talk about here. There's a multiple inlet system down at the elbow of Cape Cod. It's in Chatham. It's a really, really interesting place. Go through these slides here.
You have to click in the window with your mouse.
I have to click in the window.
Oh, click in the PowerPoint.
Oh, and then okay. No.
It's going. It's just slow.
Oh, it's slow. Okay. Well, then maybe I'll. All right. So there's a lot of images here. Let's see if I can. Oh, it is slow. Okay. All right. See, maybe I'll use the old. Well, what I'm going to try and do is show what we have here. Is we're going to have so this is 1984. This is time.com. It's really cool. They have all these images and they sort of melt together. But this is 1984, and you'll see an inlet form right here in 1987. And you can just keep an eye. Look at the whole thing. But keep an eye on this little feature right in here as we go forward. And what happens is 1987, 1988, the inlet form is getting bigger. It's got a lot of material moving downdrift. Yes, it's hanging up a little, which is unusual. And it's still forming now. This channel's squeezed. It's pretty tight. It's pretty small. A lot of pressure here. A lot of erosion. What happened is local folks wanted to do something, so they started to talk about building structures, which is very hard to do in Massachusetts. It's very difficult to build a hard structure along the coast. There's a lot of pressure. As you can imagine, some of these houses are kind of nice. So, but as the system evolved, In 2007, another inlet formed, right up in here. Now, historically, this has been the place, this is the most hydraulically efficient area. There's a big bay in here, and this is the most hydraulically efficient area for this inlet to be. Historically, it's been in there. There's a 140-year cycle of this spit elongating, becoming hydraulically inefficient, and then the spit breaks through, and the same process happens again. So you have the spit elongation, becomes more hydraulically inefficient, and then another inlet opens up. And the same thing. So everybody thought in 2007 that when this one opened up in a much, much more advantageous place, this one would close down, and it didn't. So I'm going to talk about why a little bit. All right, let's get off this slide. So these are Google Earth images, and again, keep an eye on this feature right here. All kinds of action along the coast here, all kinds of action here, but this one is locked in place. And why? Well, one thing first before we do that. So this is that feature that we're looking at. That's not moving, very shallow. This is the nautical chart, and this is from these data here from the 80s. So it's very shallow. It's a high tidal present, but it's pretty wide. A lot of water coming in. It gets really deep in here, really deep in here. But what they did was, in the early 90s, is they built a revetment right at that point. So now that shoreline is not allowed to migrate anymore. It's just pinned in there, very big revetment here. This is that point that we were looking at. And you can see it's about 750 meters long. This particular jetty has, or revetment rather, has changed the way the whole system evolved, in my opinion. This is what they did when they first did this in early 90s. They put these rocks out here. They had a bad winter. Didn't really do much. So they got bigger and bigger and bigger, and now it's this. So now the shoreline can't migrate anymore. And now all that water that's flowing in and out of here has no place to go. It has to go through this inlet, and it's gotten unnaturally deep. So look at the LiDAR for the area. This is the 2010 Topo Bathy LiDAR from the Army Corps of Engineers. It's really good stuff, obviously. This is looking north, and there's a revetment. You can see how deep this channel has got. That nautical chart in the 80s was about 8 to 10 feet at low tide. These are meters, about 18 to 20 meters. It's just digging a hole. It's scouring this area because now it can't. This normally would have eroded by now. So part of the reason why this inlet hasn't taken hold as a primary inlet is because this thing is locked in place. It's got nowhere to go, and it keeps really, really fast currents here. We don't have current data from this, but it's really, really cooking. So now we're looking west. We were looking north, and there's that revetment again. And so what we did was we went out and mapped. Now this is LiDAR. It's 1 meter grid size, and we have some bathymetry. That's 1 meter grid size. This is what that phase measuring. This is the 6205. Both same grid size. Obviously, we can tell a lot about the data here, a lot about what's going on in the processes. This is 2010. Draw a profile. That's our profile of 2010. We did the same thing with the 2014 data. We have that. Any grad students here? Which way is sediment transport going? If I ever do a textbook, this is going in here. It's going both ways, right? Bed form's going that way, bed form's going this way. It's really cool. One's flood, one's abdominal, right next to each other. And we wouldn't get this from the LiDAR, right? You wouldn't be able to tell that from the LiDAR. Now, it's 2010. It's a different year, but I can tell you, this was cooking. It's still deep. There were still bed forms here, so the LiDAR wasn't picking it up. So same resolution, but markedly different data sets. One of the things we're talking about doing now is, with these data, is using, we want to do this maybe this summer, is we can get at the internet cross-section area. Right? So you get a sense of what the cross-section is, and you can get a handle on exactly what the tidal prism is. And yet, if you have two inlets and you map both of these, you can see how they're evolving through time. Eventually, the one to the north is going to take over. It's going to become the primary inlet. It has to eventually. But mapping these on a regular basis with this sonar, is possible, because the multi-beam would take forever because you're so shallow in certain places. The 87 inlet, the old inlet that we just showed you, is very deep, and that's easier to map. The new one is very, very shallow, very broad. It would take much, much longer. But to get cross-sectional area with this, it's doable, and we're going to fool around with it this summer and see if we can go in and out a number of different times on a regular basis and see if we can see any kind of seasonal changes in these inlets. But for those of you who don't know, looking at, there's a very simple relationship between inlet cross-sectional area and tidal prism. I'm a geologist. I think everybody's a geologist. Sorry. Another thing is just by looking at these two data sets, we can see it's gotten steeper. Right, this parts of this movement has gotten deeper here, and this revetment was built when the channel was about 15, 6 meters, and now it's 18, 19. So what's going on? This is now we're starting north. We're starting north and we're going south. So the revetment's on our right, obviously. Looks good. Now not so much. It's failing. It has failed, right? This is a raw signal to the left. All these blocks are just sitting there. So it's a really interesting area. The town's very interested in this. Obviously, you saw the houses that are behind this revetment. The revetment has failed. How it hasn't, catastrophically failed, we don't know. But they're talking about sending divers down there, whether they have to shore it up. And this is part of a larger project that we're doing for the National Park Service to do some benthic habitat maps in the area. But there's so many uses for these data, especially when you overlap the imagery with the bathymetry. It becomes really, really powerful in terms of resource management, benthic habitat maps, and just all kinds of different applications. And a couple more. This is that the same embayment, very shallow area. And these features are just scour marks. They're mooring chains, the mooring blocks. They pull areas, and they're actually scooping out little holes. And again, we're talking about a meter, and really clearly, and it's funny, this is one instance where the bathymetry is more helpful than the side scan because the side scan is really noisy here because it's so shallow. So the bathymetry is giving you information that typically you do the other way around. Side scan would give you more information, but the bathymetry is so nice here with this particular instrument. And for this particular project, we're just sort of getting the incidental bathymetry. We're mapping the side scan, whatever bathymetry we get. We're not trying to get 100% coverage. That's why it looks the way it does, because we're just making sure we get all the side scan. Just a little more detail. It's another fun one. So I've been doing this for, I don't know, 7, 8 years, and in shallow water, there's not too many surprises, but we were doing this. We've got an eelgrass bed here. We're really close to the coast, very shallow water, probably 3, 4 meters, and these things are about 3 meters long. Didn't know what these were. Something's going on up top here, too, because the bottom type's a little different.
The Runa 600.
What's that? No, if it was, I'd have it in the shop right now. No, it's just, there's a bunch of them too. There are about 10 or 15. I didn't know what they were until we found out that there was an erosion control project. So these erosion control logs got eroded and worked their way into the bay. Now these aren't, no, see, I just grabbed this picture offline, but I didn't, but what we did, once we found out what they were, we got some underwater, because we wanted to find out, we got an underwater video camera. We tried to pull these things up, and they're not wire, they're not coconut fiber, they're metal. It's chicken wire. So these things are there, and this one is dangerous because it's a hazard. We went at low tide, and we got this thing with a boat hook. It's in about 4 feet of water. So the harbor master wants to know about this stuff too. So not only is it near the eelgrass beds, but it's also a threat to navigation. And just last couple slides. This is breakwater in Provincetown Harbor, and you can see we did a lot of projects for marine debris. 2 projects for mapping marine debris, locating it, IDing it using the side scan. This is with the 4125 rather. You got let's see, lobster pots, mooring blocks, all kinds of stuff on the bottom. This looks like part of a ship. And again, this thing is partially failing in different places. But then we got, what do we think this is?
Sorry, toilet.
Who said that? Yeah.
Gets paid the big bucks.
The locals. The locals throw this. This is lobster habitat. The locals throw this down. They know where it is, and they go get lobsters. And lobsters like to hide inside, and somehow these guys reach their hand in and grab a lobster. All right, that's it. Thank you. Thank you very much. One thing I want to mention, and I'm glad I remembered it, is that we are hiring. We have a bunch of different projects. I'm going to put this up and take questions. We're hiring a hydrographer. We have a need for it starting this. We'll probably get advertised in a week or so. So we are looking for somebody. And this person would be on the boat working with these instruments that I just mentioned. I am done being on the boat for a while. I need someone to come and do this. So, yeah, I'm happy to take questions.
go back to your slide with the LiDAR and the still 5 data and profiles?
Sure. Which one exactly? These?
Yeah, maybe one. Is the one with both profiles on the same?
There's not one with both. I just kind of went back and forth. But I could drag it down if you want.
No, that's all right. So you think that those sand waves, which are like, like
they're
2 meters?
Maybe a little less, maybe. Yeah.
Were there when the LiDAR data was collected?
Not these. There were bed forms there, yeah. Yeah, absolutely, because they were sandy ones.
Any reason to think that they were different? I mean, they don't really show up at all in the LiDAR data.
Yeah. I don't think, when I've looked at really, and the other thing is this is a very high energy area, so the currents are really, really fast. So I'm guessing a LiDAR wouldn't be as accurate. Because unless they did it at slack tide, these currents it's not uncommon to literally see 2-3 meters per second. I mean, it's really, really cooking in here. I got to believe that's going to affect the LiDAR. And in areas, in other places, you can see bed forms. But when you look at the raw stuff, there's just not much here at all. And this place is loaded with bed forms. And we have the Sidescan Sonar. I did my dissertation research in Chatham Harbor. There are just bed forms everywhere. It's really, really dynamic. A lot of current and a lot of sand. So I mean, you can kind of, maybe see them here, maybe.
So that's a 1 meter grid?
Yeah.
Usually they fly that stuff at 5 meter spot space.
Oh, and then they just sort of call it 1 meter?
Yeah.
Maybe that's what it is then. Yeah, maybe.
That would make more sense.
Yeah. I don't know. I'm still showing the slide saying that.
I know, it's good. I'm okay with it.
I mean, we can't do it as fast as they can. That's for sure. But we got, we can get a lot more information out of ours.
So when you showed the first slide at the beginning, it was obviously a tidal area. Why would you, I guess the question is, why would you use Sidescan to map something you could see? Or was that just to sort of develop your ability to discriminate targets?
Which image?
Your oysters.
Oh, the oysters. We want to quantify. We're trying to quantify how much area. Are you talking about why?
Well, I'm wondering why it wouldn't be easier to quantify it when it's bare, visually or with.
Oh yeah, no, that's where we did it. That's where we started. That's where we're going to do it. Is in the intertidal areas. But the subtidal is no way to quantify. So we're going to use the intertidal to get to the subtidal. I'm sorry. Yeah, to make that clear. No, it's much easier. But it's much easier to do it intertidally, but you can't go do all the intertidal stuff. You'd be there all day because we're going to just walk the areas where we know there's growth, and then walk the areas where there's no growth, and then we'll be able to tie that into the side scan, and then get at the subtidal stuff, which is obviously hard. They can go with the quadrant, and they're pretty happy with it. But if we can show that we can do it in the subtidal, then that's a whole different ballgame. Good question. I've had 2 cups of coffee, so I'm going. I don't know.
So let me ask you about the performance of that phase measuring system.
Sure.
How shallow, how far out are you getting data that you're happy with? And are you working in a meter of water, 2 meters of water?
Yeah, one of the first images that was 49 centimeters above above that. So we're working in really shallow water, and the backscatter imagery looks fantastic. We can go up 25 meters. We can go 25 meters, and it's not bad at all. We depending on what we're trying to do, we push it out to 50, and then it gets a little funky. But it also depends on the day, the conditions and things like that. But on a nice day, 25 meters, and it's a piece of cake.
That's a meter under the sonar.
In that shallow water, we can get good data. I can show you. I'd be happy to share some stuff with you. It works really well. Yeah, if I show the raw images, you'd see the depth. Should have done that now that I think about it.
You're talking explicitly about the side scan.
Side scan, yeah. But again, you saw the oysters with the bathymetry. We're in 2 feet of water, 2 meters of water, and we're getting 13, 14 meter swath, and the data are good to the far field. And quite frankly, we could probably push it more, but that was with very little hand cleaning, just to see what we had.
So bathymetry 6-7 times more.
With no hand cleaning. And normal, and say normal, I say 3 to 5 is normal for us. That's really shallow. But 8 to 1 with very little, just the basic filters and carrots and very little hand cleaning, and it's really good. Much, much better than anything I've ever seen with phase measuring units. I think they really got it. But nobody funds mapping. I hear that. I hear it all the time. I should come here. I hear that all the time. Now, this mapping's not really science. All right.
Mark, we got a question from somebody online.
Yeah.
They want to know, do surface air bubbles or micro bubbles affect the performance?
We haven't done really fine-grained sort of analysis and that kind of thing. We don't go into the surf zone, obviously. We haven't seen a problem with that, but we haven't really done. I couldn't really speak to it, I guess, because I haven't really done any kind of.
What speed are you surveying at?
Can't 4 or 5 knots, if that.
Really?
Yeah, it's got to be slow. Although we haven't fooled around with it yet. They say you can survey up to 10, up to 7 or 8 knots in this. You can go to 10 knots within the water, which is unusual. Like you can steam from place to place. You don't have to pull it out. But you know, we're trying to get as much resolution as we can. We're really shallow water, really trying to get it. So we keep it at 4 knots, 5 knots the most. But you can survey map up to 7 or 8 knots.
For anybody who's interested and doesn't know, we have the previous model of the same sonar sitting in the high bay that is ours to use whenever we choose to install it on the boat and we use it. So
Is it 4600?
4600, yeah.
How is it?
It's 2 staves less per side than this model. It's largely identical.
Yeah.
I mean, it's a little bit physically bigger, but that's.
Yeah.
So then, those erosion maps that you picked up, did you see those in bathymetry?
No, we haven't. I haven't looked. We haven't. We would. Yeah, I'm sure we would, but we haven't looked. I haven't looked. I don't process the bathymetry. I process the side scan, so I didn't actually look. It's a good question. But yeah, I think we will. Because it's such a flat bottom, it's featureless, really. So those things should jump out at you, and they're 3 meters long, so we'll see them. Yeah. Good question.
Okay, do you want any more?
All right. Thanks very